Okay, good morning. My name is Ben White. I'm an ex-PhD student from the University of Sheffield and sponsored by the UK Railway Safety and Standards Board. So my PhD was looking at low adhesion, specifically due to the wet rail phenomenon, which I'll talk about a bit during this presentation. So first off, I'm going to introduce the wet rail phenomenon, talk about some previous work, which sort of my PhD was building upon, look at the background of a model that I've been using, gather some more input data for that model, produce some experimental results to see how valid this model is, update it, and look at some future work that could be done in the future. So, first off, the wet rail phenomenon. This is low adhesion due to seemingly uncontaminated conditions. So rather than thinking about the sort of very, very obvious black leaf layer that's on there, it's looking at these low adhesions incidents that seem to occur throughout the year. But upon inspection after the incident, there doesn't seem to be any obvious sign of contamination. Looking at this data on the right, even during the autumn season in the UK, when the track is inspected after the incident, there's quite a large amount of incidents where nothing is seen on the track. And it's thought that there's two main things causing this. Low moisture conditions, so rather than heavy rain, we're talking about drizzle, dew in the morning, and damp conditions, and also the build-up of debris on the railhead. My PhD was looking at iron oxides and whether these iron oxides could be building up on the railhead and causing the low adhesion. And actually found that when you form a paste, at least in small-scale simulations, this paste can produce very low adhesion conditions. So some of the first work that was done on this was in 1976 from Beagley's paper, and he found that a combination of wear debris and small amounts of water on a twin disc test rig could cause low adhesion conditions. And he produced some data up here, which has been recently redone by a virtual vehicle, and it shows that when wear debris was removed, you get higher adhesion, as expected, rather than when there was a build-up of wear debris on the railhead. And he actually used, as well as the wear debris, he used pure iron oxides. This was hematite in this case, and he produced a small model extrapolating from this data and looking at the material properties of these pastes on the railhead. So he used iron oxide and hematite and also leaf debris. He looked at the shear strength of this material and the layer thickness when it was under load. And he produced a model that he claimed showed that very low adhesion was caused, very low traction under certain material conditions. So I wanted to look a bit more into this. Recently, Virtual Vehicle has updated this model. They've actually, whilst Beagley was looking at it for a twin disc test rig, they've actually used it for a high pressure torsion rig. They've updated this model using, once again, hematite, type of iron oxide. And they based all this, some of the input values for this model was based on parallel plate plastometry. So this is a very, very basic schematic of it. You're compressing material between two parallel plates under a certain load, and you're looking at the separation of the plates under this load, and from that you can get the yield shear stress of it. These are some of the input values into this model, and what it showed was that for certain solid oxide fractions, this is by weight, as you increase the amount of solid oxide fraction in a paste, the adhesion coefficient would remain fairly static until a certain point at a very high solid oxide fraction, where there would be a very clear minimum in the adhesion coefficient. And then it would rise back up again when a certain dry value was reached. But all this data was based on these 1976 experiments, so I wanted to not only repeat those to generate some new input values, but also generate some experimental data just to see whether this model was valid. So first off, I was generating some new input values. I used a very similar, slightly more modern version of the equipment that Beagley used. So again, it was two parallel plates. I used a hematite paste between them and created multiple hematite pastes. I did it in a percentage, so a weight percentage of hematite paste. So for instance, 10 grams of material at 70% would be 7 grams of hematite powder and 3 grams of 3 grams of water. Compressed it between these parallel plates and applied a torque to it. And from this, we could see the viscosity with increasing shear rates, and also we could get the yield shear stress, which is the input value into this model. or one of them. So, yeah, on this, we could see that the material, surprisingly to me anyway, was shear thinning, apart from these sections under here where at a certain shear rate, shear thickening occurred. But for the input value, for the input into this model, we're using the yield shear stress, which is essentially the torque needed to first yield this material. So we could add that in and update the model. But I suppose most interesting for me and most valid for the PhD was this experimental data and whether this model was valid. So for this, I think you've heard quite a lot about it at this conference, but this is our Suros twin disc test rig, or a schematic of it, and it's 2 counter-rotating steel discs made of wheel and rail material. For these conditions, you use 2% slip, which in this case was saturated, and 1,500 megapascals. And for this, I added iron oxide paste made to different weight percentages into the contact using a syringe, 2 mils a minute, as these discs were rotating, and just looked at the traction coefficient that was produced. Up here, for the red line, we've got 100% iron oxide powder, so that was simply the dry powder being added into the contact. Under this, the blue line is pure water, so I took that as 0% iron oxide. And underneath here is some data from 30, 40, 50, 60, and 70% iron oxide. And from this data, it seemed that the more viscous the paste that was added, the lower the adhesion coefficient that was produced, the traction coefficient that was produced, up to 70%. And at this point, I had real issues actually adding this paste to the contact. It was incredibly viscous. It was hard to apply. It wouldn't go through the syringe. And also, unlike the lower percentages, which were sucked into the contact, at 70%, it simply bounced off. So this is why the orange line not only, well, I couldn't look at this, it stopped early, but also there's a large fluctuation in the results. When it did actually enter the contact, we got a very, very low adhesion minimum of 0.02. But while the rest of these were easily repeatable, that one could not be. So here's a box plot of the results. As you can see, as expected, the traction coefficient was reduced with increasing weight percentage of hematite. As we go down to 70%, and then for 70%, the minimum is very, very low, but the actual average is a bit higher because it couldn't all enter the contact. And then once again, rising back up to the dry valley at 100% iron oxide powder. I've plotted this against my best fit of the model, and this was tweaking the model from a high-pressure torsion rig to the Suros rig as much as possible, and plotting it alongside these results, just to see how it fit, really. And there's 2 big differences here. The first one is that the adhesion minimum is skewed over to the right-hand side, which could be easily changed. And then the second big change is that whilst the model predicted that there would be a very obvious adhesion minimum and then quite a high traction coefficient either side of this, we've got a much more gentle decline. And this could be, for instance, due to the preferential squeezing out of water. So when I add these pastes to the contact, it's not necessarily the paste, or it definitely isn't the paste that actually is found in the contact itself. Water's squeezed out, and that's evident by a build-up of iron oxide layer during the tests and obvious after the testing on the specimen discs. So essentially, the viscosity is increasing in the contact. Just to talk about some other results and other testing that has seen similar effects of low traction when iron oxide pastes are added to the contact. This one over here is from another University of Sheffield student. This was actually on a Pardubice test rig. And this is essentially a much larger twin disc contact up on this left-hand side. And we could see, or they could see, this very dark band of paste that was in the contact. And when that was produced, seemingly from wear debris and a build-up of iron oxide, there was very low traction produced. These 2 are my own testing. They're just video screenshots, that's why they're a bit blurry. On the right-hand side is some hematite testing, like I just talked about. And on the left-hand side is a naturally produced iron oxide layer. So I produced it just using the heat and pressure and small amounts of water in the contact. And when this was present in the contact, I also got very low traction. On the top right over here, is a railhead that I was visiting early in the morning. There was dew on the track. And actually, when you rubbed the railhead, it was clear that this paste was present on the railhead itself. So it sort of validates that these pastes can be found in a real situation as well. So I've used this method to basically create a method to simulate the wet rail phenomenon, which we couldn't do before. At least we couldn't produce the wet rail phenomenon using just iron oxides, but also we couldn't get these very, very low traction coefficients that we're seeing here. This is just a snapshot of the work that I've done, but I've changed the contact conditions and seen how that varies the traction coefficient. I've tested mitigation methods such as traction gels and seen how they can mitigate this wet rail phenomenon. And I've used different types of oxides which have had different effects on the traction coefficient. And I would like to validate this using some full-scale testing, just to see whether these very low traction coefficients we're looking at on the small-scale rig actually occur on both large-scale rigs and in the field. And then this is just finally looking at the bigger picture of all these pastes and things that seem to cause the low adhesion. This is on the railhead, just the iron oxide pastes that I've been using. I've also produced low adhesion on the twin disc test rig using clay. I've heard it's been produced as well using coal dust. And then on this left-hand side, these are different organic compounds also found in, these are thick gels basically. So using pectin, carboxymethyl cellulose, and Arabic gum, which are all thick gels that can be added to this twin disc testing. All of these also seem to produce low adhesion. So it's really just thinking, okay, maybe we should be looking at the material properties of all these pastes and gels that are added and using rheometry a bit more in our work and seeing whether there's a correlation just between the viscosity and the traction coefficient that's produced. And this is finally a leaf layer that are found on the railhead. Under wet conditions, it also seemed to produce a very viscous paste. So this is what we could be looking at as leaf layers, that it's actually the paste causing this low adhesion rather than the standard solid layer that people are looking at. So just to conclude, during this work, the wet rail phenomenon could be simulated on a small-scale test rig. The pastes that cause low traction on this Suros rig are similar to those that have been seen on the real running band of rail. This has been documented in the 70s, but not repeated until recently. This work, along with the previous work, can be used to update this model. And the adhesion model and the experimental results shown here can be used as a tool to analyze how adhesion varies with contact conditions. So, okay, thank you. That's me done.